The last subject about volumes is called volumes by slicing. So it's a little bit more general because of the way it's set up. We're not looking necessarily at something that's a solid of revolution, but what we're looking at is something for which we can figure out the cross section. So we kind of have done this with solids of revolution because once you have the solid of revolution, you can figure out that the cross section because you know that it's a washer or a disc, right? So we basically did that. But if you want to be more general, you can look at some kinds of solids that are not necessarily having that circular cross section of the washer or the disc. But if you can figure out what the cross section is, then you can still do it the same way. Essentially, if I've got something, well, here, I have some bread, right? Okay, so the bread here, right? Say this is our solid. And let's say, though, we know the formula for the area at any particular point. Like, let's say I know that this is some, let's pretend it's something that I know. Like if I know how wide this is, let's say it's regular enough that I can figure out the area. So then I could just slice my bread, and you see this is not a sliced loaf yet, so fine, but I could slice my bread, and for each slice, I could figure out the area because I had some formula that I knew what that was. Okay, so that's the general idea. And then if you do that, you just add up all those areas. So what that's going to look like is, if you know what the area, so that's always the kicker, like how do I know the area? That's why you don't do these very often, because most of the time you don't. If area of X is the area of a cross section at X, then I can look at the volume by just adding up all of the cross sections, right, from wherever, from X1 to X2. So where can you actually do this? Usually it has to be some kind of solid that has, I guess, something that's kind of made up, right? So it's sort of interesting, and they'll give you, for example, they'll describe it in words, and you'll have to kind of either imagine it, or if somebody's nice to you, they'll give you a picture, which is going to help, right? But for example, in the book, they do one where they say, and I will do this problem, but I want to illustrate it for you first. The base is a circle, perpendicular cross sections are equilateral triangles. That's an E. Okay, so you're like, what the heck is that? So I found a picture. Here we go. This is actually what that solid looks like. And in fact, this person 3D printed this so that we could see what it really looks like. So it doesn't necessarily look like a circle from this perspective, but if you looked at it straight on, you would see that this is a circle. And she used the circle of a radius 5. So she used x squared plus y squared equals 25 as the circle. And then what happens is that any particular slice of the circle, like you can see right there, or this one here, let me draw a circle. I'll get rid of this. So you're going to look at that, which is the base, and they told you they were equilateral triangles. So whatever that is the base, it's also this here. So this is what that solid would look like with a certain amount of triangles, and then you can imagine what it would look like as the number of triangles went off to infinity. So we can use this method of finding, so we can actually compute this volume. Let me go ahead and do it. Okay, so this is the idea. I've got these triangles coming out of here. In order to do my integral, I need to figure out the area of this triangle. So here's 5 and here's -5. I'm going to go, say, from -5 to 5. And out of here, you can imagine from the picture, there's a triangle coming out. So let me draw that triangle. The triangle is coming up. Let me draw it bigger. Sure. Okay. So here's the triangle. It would be coming out of the blackboard. So, and it will go from here to here. So that's going to tell me, with respect to the variables of the problem, x and y, this distance is y, right? So the base of the triangle is going to be 2y. It's going to be y in each direction. Okay? Now, they also told you it was an equilateral triangle. So this is 2y and this is 2y. So what's the area of a triangle? It's 1/2 base times height. I know the base is 2y. I have to figure out the height, right? So here's my height. But they also told you it was an equilateral triangle. So if I look at this, it's like a 30, 60, 90 deal, right? So this is here. This would be 1y. This would be 2y. And then h would be square root of 3y, right? Because this is 60 degrees, or pi over 3, and this, yes, I said it right. And this is 30 degrees, or pi over 6. Yeah, got it. Right? Saying the right thing, just make sure that I'm keeping it straight. So from your knowledge of basic geometry, or you can go ahead and, you know, if you forget, like you can figure out sine, cosine, whatever, but you can figure out that this h is square root of 3y. So that's going to tell me that I've got 1/2 times 2y times root 3y. Oh, that looks terrible. Let's put it down here. These two cancel. I have square root of 3y squared is my area. Okay? But I need it in terms of x, because I'm integrating with respect to x. So that's not that bad, right? Y squared is 25 minus x squared. I can solve for y, or I can just solve for y squared, because it's y squared here. So this is square root of 3 times 25 minus x squared. Okay? Now I put that in, it's there you go. So -5 to 5 of root 3 times 25 minus x squared. Actually, if I want, I can even take it from 0 to 5 for symmetry reasons, because it's going to look the same on either side. But it doesn't matter. You can go from -5 to 5 if you want. This integral is easy enough to do. I end up with 500 root 3 over 3. Because I started with a radius 5 only because the lady that made the 3D printed one, she started with a radius 5. She made it in Mathematica or something. It's kind of cool, but I don't have a 3D printer. Okay, so I want to do one more question, one more. But I'll show you I found another picture. I thought that was kind of cool. let's see here. Let's find that picture first. What did I do with the picture here? Oh, well, that's too small. Okay. So here's another picture that he actually made the models not with a 3D printer, but just literally with paper. And what he did here is he started with the curve y equals x squared from 0 to 1, and then he filled up the perpendicular cross sections with just some different shapes, right? So these are obviously circles, right? Half circles. These look like squares. I think he's got some triangles here. Like the right, it would be a right triangle. I mean, presumably we could do it also with the equilateral triangle. And these are rectangles. In order to do the problem, he can't just say a rectangle. He has to give you a little more information than that. So he would have to give if we wanted to actually compute this, we would have to know the ratio of the two sides, for example. So you need to make sure there should be enough information in the problem to do it if you have to do one of these. But the trick is, of course, not only to figure out that area, but also some of these can be quite difficult to picture, right? And I'm not sure, I don't know really how easy it is to make them with any kind of like graphing software. I think because you don't have a formula, it's kind of difficult. So we can try to do, I figured we'd do this first one here with the circles, because not only is it not terribly difficult, but also it's bigger here, you can see it. So let us get rid of that. And this was the picture, the base of the solid is the area between y equals x squared and the x-axis. And it looks like he drew it from 0 to 1. And I'll see if I can link those for you in case you want to take a look at them again. The perpendicular cross sections are, I don't know, half circles, right? Okay, so the base was just this. Okay, this is y equals x squared. And so at some point x, you have this half circle, which you can't see because I didn't draw it well, but let's bump it out and draw it well. So, okay, it looks terrible. All right, close enough, right? So at the point x, the height here, this is going to be the diameter of the circle, right? So this is our y. Okay, that's the height to the parabola. So we know that that is x squared. So we have to figure out what the area of this is. So that's not too bad, right? Area of the half circle is going to be 1/2 pi r squared, right? Now we know the y is the whole distance, so we want the radius to be half the distance. We can see that the radius then is y over 2 or x squared over 2, right? Because the radius, the whole distance is going to be the diameter. And then we just can plug that in here. So I'm going to end up with pi times x to the 4 over 8. And so that's my area. So if I want to find the volume of that horn-shaped object that he made, I'm going to take x from 0 to 1. I'm going to take a of x dx, and a of x is just pi x to the 4 over 8 dx, right? So I've got my pi over 8. I integrate x to the 4th. That gives me x to the 5 over 5. Evaluate from 0 to 1. I get, what's 8 times 5 is 40. So pi over 40 units is my answer. The actual integral isn't hard, but sort of figuring out the geometry can be tricky for these. There may be, I think there's one on the worksheet. There may be one on the WebAssign. These aren't the most important kind of problems to do, but they're kind of cool if you look at them and sort of think about them. So I wanted at least just to touch on it.